Our first speaker today is Melanie that will give her second talk of a series of talks about counting number fields in families and pointwise.
Okay. All right. Right. So this morning I'm going to talk about counting number fields. So let G be a finite permutation group. And K a number field. Little k here. This will be maybe I will I'll try to make my little k's curly. It'll be the base field. There will be a capital K playing a role later on. And so here is the asymptotic, the counting function of whose asymptotics we're interested in. So I want to count extensions of the base field. Will not matter at all whether you mean in a fixed algebraic closure or isomorphism classes, where the Galois group of their Galois closure is isomorphic to G as a permutation group. The permutation is action is on the maps from L into L tilde. If you haven't seen this notion of a Galois group, a permutation group, feel free to think just about the case where L are Galois extensions, and this is just an isomorphism of finite groups, but this is a convenient setup that allows us also to talk about counting non-Galois extensions with specified Galois closure and structure inside that Galois closure, like which subgroup of the Galois group of the Galois closure are they the fixed field of? Okay, in any case, so we're counting such things with the, okay, all right, I'll write the norm of their relative discriminant. So that's an ideal. You take the ideal norm to be at most x, but because I don't want to always have to write so many letters, I will write this as just d L over k later. Okay, so we're saying I want to count extensions with this Galois permutation group of discriminant, or norm of discriminant, bounded by x. And the question is to understand the asymptotics of this as x goes to infinity. And
I think you want the terminology of that set, right?
Oh, yes, to call it in. Yes, thank you. Thank you. Sometimes we define the set is sometimes useful, but for this talk, I can just take the cardinality. Thank you. So then we have Malle's conjecture, which is a conjecture about these asymptotics from papers in 2002 and 2004. I will just say in the conjecture, Malle gives explicit functions, which I'm not going to write here just because it's not so important in this talk, but they're not so hard to write down, of the Galois group, and then of the Galois group in the base field, and then he, after he writes down those explicit functions, he conjectures that for all such G and K, there exists constant C such that this counting function of G extensions is asymptotic to a constant times power of x as he's specified and a power of log x as he's specified. Now, since I didn't tell you what A and B are, it might seem kind of perverse that I did these weird things to them, but for people who know what A and B were, if I had called this number A and this number B, they would be very mad. So, in any case, so, and this here means this asymptotic means that this notion, I mean, the ratio goes to one of these two things, the counting function and this function of x, as x goes to infinity. Okay. So, there are many cases of this conjecture known, and I am not going to go into that. There's in section 1.4 of a recent paper of mine with Brandon Alebrts and Jiuya Wang and Lemke Oliver that I'm going to refer to a lot in this talk. We have a long history of the results on this, but it's already out of date because people have proven some wonderful theorems since that paper appeared. But in any case, there are many G's for which we understand and know that this conjecture is true. So sort of proven. I'll just sort of say proven in many cases, and it is also false in some cases. So Jürgen Kaluners, who is here in 2005, gave a counterexample. He showed that it was false in the case that G is C3 reads C2, Reith product of cyclic groups, that in particular there exists more than predicted. So if you would like a conjecture that might be true, you need some kind of modification. So for fixes, so originally there was improvement, a suggestion that overcomes some of the counterexamples due to Chaire and then Jiuya Wang has a recent paper kind of showing counterexamples to Chaire's fix, and I would say sort of see this for the sort of most updated conjecture we have on this so far. The issue is a lot around this B. So in order to not dive too much into those issues, I'm going to help Malle out a little bit and say, what if we are just agnostic, like he was about the C, about the B? And if you introduce that agnosticism into the to the B, which you don't have to. If you really want to understand the B, you can think about it. But for and it's important, interesting. But for the purposes of this talk today, I will just simplify our lives by thinking about this version of the conjecture. All right.
When you talk about the conjecture, do you also mention what this happens?
They are in my notes to make a comment at an appropriate place. Yes. So thank you for reminding me of that. Okay. So. All right. So now I want to say. Yeah, so when I say here, the sort of, I mean, maybe I shouldn't, when in this shape, okay, I don't know if that was an objection to this, sort of in the shape that was previously above. Okay, all right, so now I want to talk a little bit about how you might, how you might think about, like, how should we guess what the size of this counting function is. I'm going to give a very simplified version of the Malle-Bhargava principle, which is a way of thinking about these that comes from both Malle's original papers and then a paper of Bhargava in 2010 on mass formulas. The principle is not so precisely articulated in grand generality in either of those places, but you can certainly see that is the way that they're thinking, especially in this simplified version that I'm going to describe here. So this counting function, in it is counting these global objects, these number fields, and because I chose here this, especially because I chose this isomorphism to G, this is counting surjections from the absolute Galois group of the base field to G. So this here, I'm writing GK for the Galois group of K bar over K. And these global objects, they restrict at every place of K to local objects. In particular, I'm going to think about the restriction to the product over primes of K of homomorphisms from the inertia group at that prime in to G. So this absolute Galois group for every prime of K has an inertia group. I'm writing that as IP. Maybe I'll write over here, IP inertia group. You can make a choice of inertia group at P, and then you restrict the map to G just to that, and now it might not be a surjection, of course. I mean, if P isn't ramified, it will be a trivial map, but so that's why I just said a homomorphism. And you may be disturbed that I picked an inertia group, so I will just take this image up to an equivalence by G conjugacy, so that this now does not depend on a choice of an inertia group. If you picked a different one, it would be G conjugate. So, all right, and I left some space to write one more thing, which I will write in a second. What do I have? Okay, sorry. We'll remind you over here of the inertia. And I want to say one more thing about this restriction to all the local inertia groups, which is that this function, this discriminant that we were counting by here. I mean, this doesn't see, there's nothing in this notation that says, that includes the x, but each of these has a discriminant that's relevant as to whether or not they're counted by that counting function. And the discriminant that we're counting by here can be detected by the image just of these restrictions. The discriminant only depends on what inertia does everywhere. So it is a product over each prime of a dp that crucially only depends on what you see down here, what the restriction was for p. And so the kind of speculation behind the principle is what if the fibers of this restriction map were on average constant size. Because while this is very complicated, the absolute Galois group of K we don't know very much about. These local inertia groups we understand much better. Certainly, if we understand them very well at all the primes that are relatively prime to the order of G, they're maps into G, because that just is a function of the tame quotient of the local inertia group. But even in the non-tame case, we understand these things really well. So here's this thing that we don't understand, and we've kind of mapped it to a thing that we understand, and maybe they're kind of the same. All right, that's the idea. Now, there is one thing, which is why I left some space here, which is, of course, in between restricting to the inertia group, you could restrict to the entire decomposition group, and not every map from the inertia group could have come from such a restriction. So I will write here, this is a sort of poor notation, but it will just remind you that it should have been a homomorphism that is a restriction of a homomorphism from the decomposition group, okay? Because that we clearly need to be sort of mapping into that set, and then you need that for this to sort of plausibly make sense. Okay, so this is the kind of like, okay, look, now we understand this, we don't understand this. What if we make a guess that they're somehow simply related? And then, so like I said, this bottom piece is something that is very easy to understand concretely. For example, if we make a Dirichlet series to count the objects on the bottom, so it looks like the following. We sum over these homomorphisms that are possible from the local inertia group, and we and then again, like I said, this discriminant is a product of the local discriminants, each of which just depends on this. So I'll write that as kind of d phi here to the s. So then this is a Dirichlet series, and then when you sort of multiply it out over primes, you get as a coefficient of n to the s all of the tuples of local objects here that would have discriminant s. And all right, and now, okay. As I mentioned, this is particularly easy to understand at primes that are relatively prime to the order of, that are relatively prime, prime to G that don't divide G, and that's most of the primes. So, okay, this is an Euler product. There's a few bad factors that I don't want to talk about. That's what's encapsulated in these quotes around this equals. But other than that, because of our very good understanding of the local absolute tame Galois group, this is can be written as very concretely as a sum over conjugacy classes of elements of G that are the same conjugacy class of that are fixed by powering by the norm of the prime. So that just comes from the relation in the absolute tame Galois group of local fields. 1 over the norm of prime to the s, and then I need to encapsulate here what was the exponent, right? So this local discriminant, it's some power of the prime. What power is that? It's a function of where we set inertia. This is where we set inertia, and this is this function in y. So this is the discriminant exponent for primes of inertia type y, which you can express very simply in terms of the permutation group structure. It's the degree of the permutation group minus the number of orbits, but not so that's also very concrete. But also maybe another good way of thinking about it is it's just whatever exponent you put when you make the discriminant on primes that were ramified with that kind of inertia. Okay, so this principle. Okay, so then this is like a super concrete Euler product whose asymptotics and partial sums of coefficients we can understand very well, and then if you add, like, oh, maybe the fibers on average are constant size, so this then with the analysis of this function, in fact, implies, this guess plus the analysis of this function implies Malle's conjecture. In fact, like without the star, the original Malle's conjecture with the A and the B. So that's another way of thinking about where the A and the B come from, like very closely related to how Malle came up with them in his original conjecture. Yes?
Are there different kinds of bad factors, or they're only look like the same thing?
You mean the factors that I haven't written because of this? Yeah, there are different ones. Yeah, there can be different ones at any of the primes that divide
Do they
G.
represent anything interesting?
Well, they represent all the different possible local behaviors of the primes that divide G in G extensions. And so, yeah, absolutely, they're interesting. But they do not, one part of the reason why this lie is okay is because they do not affect the asymptotics of the partial sum, except for in this completely ignored constant. But absolutely, they are relevant. And if you want to ask, you have some prime that divides the order of G, and you want to apply this principle to ask something about behavior at that prime. Those factors are both computable and relevant. Yeah, great question. So now when I have stated it this way, it's clear that this principle can be extended greatly. Wait, where was the? Okay, the principle can be extended greatly. As I said, this is a very simplified version of it, as we were discussing here a little bit. If you maybe wanted to impose some local conditions, that means you only care about subsets here. So then you would just replace this sum with just the subset that you care about, and then you see what you get. Or you also realize here how agnostic this whole principle was to the fact that we were counting by discriminant. All that it cared about was that we were counting by something that could be detected by what happened on the local inertia groups. So you could replace these exponents that say, well, what exponent do you put on P in the discriminant with some other exponent that depends on the image of inertia. Okay, so this can be extended in many directions. Including counting by other invariants. Of the form product over ramified primes, where you take the norm of that prime to some exponent that depends on the image of inertia. So this is just some function. Here it was some, some particular discriminant exponent, but you could take, some other exponents of your choice. Indeed, Malle's conjecture already does this. It already counts these Galois, it already counts fields by multiple invariants, because in this permutation group form, when you're counting a non-Galois field that generates its Galois closure, you could have just as well counted its Galois closure. So indeed, Malle's conjecture already, you could, instead of thinking of it as counting all of these non-Galois fields, you could equivalently say Malle's conjecture already counts Galois fields by several invariants, which are all discriminants of subfields that generate the Galois closure. Just for example, when G is S3, you could count S3 cubic fields, whether you're thinking of the three-dimensional one or the Galois one, it doesn't matter. They're the same information, but you could be counting them by the discriminant of the cubic S3 field, or you could count them by the discriminant of the sextic field, and those are just sort of two different ways to count the same thing. Okay, so, all right, and now, so anyway, there's a strong reason that this is a principle and not a conjecture. In particular, as I said here, it implies Malle's conjecture, which we said in counterexamples. So it's not a conjecture, it is a sort of baseline way of thinking that can be refined in many directions. One thing that you might notice also is another kind of way in which you might extend the principle is, you could think, well, maybe it gives some insight into the constant, because you can certainly understand the constant in this asymptotic counting, and okay, there was some kind of ambiguous constant here, but maybe you could understand that, or and indeed, that is the reason that that Bargeville was considering this way of thinking, is he was trying to predict the constant in counting degree n Sn extensions for every n. So another direction in which the principle can be extended is to think about the constant. And so here that I want to say in this this context where we're now in this generality of counting by any kind of invariant, and we're interested in the constant. And you think, well, this sounds like a really great principle, but what about something that was like this, except we thought it might make correct predictions all the time? I now want to refer to the beautiful recent work of Loughran and Santons from 25, which sort of is I will say, a serious sort of upgrade on this principle, such that you could expect it to make correct predictions, and in particular, especially on the constant c here, and and various invariants. Okay. All right. So okay. Now this. So we see here now that we could potentially be counting number fields not just by discriminant, like in the original conjecture of Malle, but by lots of different invariants. But these, I just want to say, these aren't all the ways to count number fields. There are other ones, particularly I want to call out Fabian Gunluck's recent, not a few years ago now, paper suggesting maybe like counting by all of them at once. So not only would it be interesting to count by any of these in particular, but you could try to say, well, what if we pay attention to all of them? I want to disagree with Jordan and say that there's no correct way to count. There are many different ways of counting, and they are useful for different things. I mean, the discriminant, there's a reason the discriminant is a very natural invariant. There's a reason it has come up. It's a polynomial invariant in the structure coefficients of the ring, which is why we see it in homogeneous vector spaces. In the function field version, it is, more or less the genus, which is an incredibly natural variant. The discriminant is very natural. The product of ramified primes, where you just take all of these weights to be 1, it is one of my favorite ways. It is a very fair and balanced way of counting, both colloquially and in the technical senses of both of those terms that have been introduced in an old paper of mine and in Loughran Santons. But for different reasons, there are many different ways that you might want to count. In fact, it's so complicated in all the ways that you might want to count, and what we might know in each case, that there's going to be a conference at ISERM in June just to kind of try to compile a database, a sort of more sophisticated computational database to understand what is known. Okay, so now I want to talk about a perspective on how you might do some of this number field counting, in particular, by discriminant, but also by other counting functions. And so in a framework that in a recent paper we call inductive methods. So this is the framework is described in our paper, so with Brandon Alebrts, Lemke Oliver, Robert, who is here, Jiuya Wang, who is here, and it comes from the various. It comes from the very simple observation that these groups, these Galois groups that we're counting by, most of them, well, I guess they all in some trivial sense, but groups have subgroups, right? That's the starting point here. So if I have some group G, maybe it has a subgroup H. Of course, this is most interesting if H is a non-trivial proper subgroup. And most groups have such non-trivial proper subgroups. And so that means that in the Galois diagram, if I was counting Galois G extensions, which now is, I kind of pointed over here, you could shift Malle's conjecture to think it's all just about counting Galois G extensions with different invariants. So while I won't talk about the invariant we're counting by for a while, you can just say I'm counting Galois G extensions. But such Galois G extensions, they're also H extensions. They're H extensions of the H fixed subfield in the Galois diagram. So, a G extension L over K is also an H extension L over big K. All right, so perhaps you'd like to count G extensions, but you don't know how yet. But suppose you're good at counting H extensions. So suppose you are good at counting H extensions, then perhaps you can count those H extensions. So for each capital K, you could count the H extensions, so the number of L over K, and then you just sum that over the possibilities for this K here. Then maybe you could count all your H extensions over each of these big K's, and then add them all up, and do this to get a count of G extensions. Now that sounds wonderful. And there are, of course, obstacles to making this work, and I want to sort of isolate two of the issues with this kind of naive approach. The first one is that if you fix some big K that might appear in such a diagram, and you look at all the H extensions, they're not all going to fit in a diagram like this. They might not be G extensions of the base field. So not all L over K H extensions give G extensions. So, I mean, that was kind of ambiguous in what I wrote here, but basically if I mean the L over K's that could appear in such a diagram, then it's not just that you have to be, somehow good at counting H extensions, but you have to know which ones to include. And then the second thing is that you need to do the sum. You need to do the sum, including error terms. Even if you were, you thinking you were good at counting H extensions, maybe you thought, well, I get an asymptotic main term, but then you also have an error term, and then maybe you're doing an infinite sum of those error terms. So that certainly it presents a challenge to this. So what I'm going to say about this second issue is that obviously here you need some combination of being, I'll say, decent at counting the bottom extensions, capital K over little k, and good at controlling error terms. And there's a sort of trade-off here that the better you are at one, the less good you have to be at the other. When we employ this outlook to count and get many new cases of Malle's conjecture, for example, we are doing it in a setting where all we need are sort of weak upper bounds on being able to count these bottom extensions. So it's not like, oh, we need to be able to prove Malle's conjecture for something like the bottom extensions. It's much weaker than that. But exactly how kind of what sort of information you need about the bottom extensions certainly depends on when you were counting your top extensions, how good you were at the error. Right, so that's what I'm going to say about addressing issue number 2 in the strategy. In this approach, and I'm going to discuss I'm next going to discuss 2 different ways to address issue 1 that we consider in this paper referenced here. So I'll say first, okay, strategy 1A, so it's 1 because it's addressing this issue. So this is the first strategy to kind of address the situation that not all of these extensions give G extensions. And to describe it, I'm going to enlarge this Galois diagram to include some possibly other auxiliary subgroups that I will use. So we have 1 H G. I'm going to take a G prime and an H prime. Okay? So what does the field diagram look like? I have my L, my big K, my base field, and then I'll take a big K prime and an L prime here. So I have this whole field. And okay, you could say this in terms of the groups, but somehow I feel like we're all more comfortable saying things on the field side. So if you construct such a Galois diagram such that L is the Galois closure of L, the composite L prime K over K. So L is the Galois closure of the composite of these 2 fields. That's obviously just a statement about the normal core of the intersection of some subgroups, but maybe you prefer it on the field side. So in this case, in this setup, this sort of number of these extensions, L over K, that we're interested in, we could think about by summing over K prime the number of L prime over K prime, just because if L is determined by L prime and K, for the L's over K then are determined by simply L prime. Now, this seems, there's a lot of groups in this. That's the hard part, I guess, here. Jordan was in a train.
Very straight. See if it's a bit slanted, and I feel like it's easier if it's like completely horizontal.
I can try it.
You wanna work on that? I'll go over to this next one. Thank you. All right. It might have seemed like I introduced a lot of subgroups into this picture. But one reason that I decided to even do this in the talk is to give you a little bit of a sense of the flexibility of this outlook, which is you can try to do this method when you're counting G extensions. You can try it for all different sort of combinations of ways of constructing these fields like this. But in particular, okay, what's the key point of this strategy 1A? So the key aspect of this strategy is to build a situation where you expect, so you want to pick these groups such that you expect most L prime over K prime to give the group G. Okay? So I could have said up here, like, okay, in our original diagram, let's try to be in a situation where, most L over K give the group G, but that is overly restrictive, and perhaps it sort of never happens or at least not a lot in interesting cases. But with this kind of flexibility, where you have sort of more groups in your diagram, you can cook up a lot of situations where you can count extensions where you expect most of them to give the desired full Galois group. So I'll sort of give, just to show that this isn't like the craziest thing in the world, this sort of pentagon diagram in a special case where the group is D4. So I'll like write D4 as permutation group 1, 2, 3, 4, and 2, 4. So like symmetries of a square. Right, it has an index 2 subgroup given by the group generated by the transpositions, an index 2 subgroup in there given by one of the transpositions. So I'm drawing a Galois diagram over here, and it's that pentagon. And here I'm going to just put this same subgroup. So it's a little bit perverse drawing it here, but this is the same subgroup here. Because I didn't say, this has a lot of flexibility. You can, for example, choose these to be the same. You don't have to. All right, so now this, when we translate this, there are L primes and the K primes, and we expect most of them to give this group. What does this mean for this diagram? This star sort of strategy point here comes down, in this case, to the fact that most quadratic extensions are D4 quartics, which is a very classic and important observation in counting D4 things. So of course all quadratic extensions have Galois group in the wreath product, which is D4, and so you might expect like most of them would be the whole thing. So Cohen, Diaz, and Olivier used this in 2002. So this is this is going back to the time of Malle's original conjecture to prove Malle's conjecture for D4 quartics by discriminant, so this is sort of the first of example in this line of this strategy, and I'll say that there are like many other papers that use something that is in this strategy beyond this, that you're not going to be able to sort of talk about all, but I want to particularly mention Jürgen Kluner's work on counting Reith products of quadratic extensions of other fields, so C2 Reith B. In our paper, we do some Reith product counting, and then in much more sophisticated versions of this than those, I would say, in the D4 case, especially are in the papers of Altung, Shankar, Varma, and Wilson, and the recent Shankar-Varma paper, I think Ila's here, back there, that count D4 Malle for D4 optics and D4 by other invariant, the Arn conductor of the two-dimensional representation of D4. Okay, so that's sort of one example of to sort of say, okay, this strategy isn't so crazy, but this kind of thing that you could do all the way going back to Cohn-Diaz-Olivier, you can sort of apply it in many more situations, including ones where these two groups aren't the same, and get further counting results, including many more cases of Malle's conjecture. Okay, so, but I want to discuss now also another way you might approach issue 1. Maybe instead you could be of concocting this setup where most of the time the extensions you're counting give you the whole group that you wanted. You could instead be really good at counting H extensions enough that you're such a master of counting H extensions that you can detect, as you're doing that, enough to detect the full Galois group over the base field. You're like, well, I really know all my H extensions, and I can tell you everything you want to know about them, including if they happen to have full Galois group G over the base field. So it turns out that we're really good at counting abelian extensions by class field theory. We really understand what they are and can even understand things like the Galois group over a lower field. And so there's a lot of work on this going back to Wright. And one of the most recent sort of indications of how really good you can be at counting abelian extensions is a paper of Julie Tavernier, who is here. Also, I want to mention that especially in this aspect, I want to mention the paper of Alebrts O'Doherty from 21, where they actually introduce a new notion, which they call twisted Malle's conjecture, which is precisely about counting H extensions for a general H, such, where you restrict to having a Galois group over a lower subfield. So this is particularly relevant to this aspect. So in this work with Alebrts and Lemke Oliver and Wang, we apply this kind of strategy when H is abelian, though it's very interesting. The other obvious case where, we, and by we I mean people like Frank and Avril Shankar are very good at counting extensions, is in the H equals S3 case. So it is interesting to wonder in the sort of twisted Malle's conjecture version where you need to count with the detection of the Galois group, if we are that good at counting S3 extensions or not, that's something that would be nice to know. Okay, so that's what I wanted to mention. The other way that you could sort of get around the first issue is you really know your H extensions. So this this kind of approach, especially I think what I'm going to mention. So with this kind of approach, we prove many new cases of Malle's conjecture, in particular for counting by discriminant. And I'll just mention some sample corollaries, kind of, or special cases that we get, especially that come from this strategy 1B. So we get that Malle's conjecture, okay, either sort of with the correct B, that's what that star meant, either the agnostic of B or you could say the correct B version holds for any G nilpotent such that the elements of minimal that give minimal discriminant exponent when you have that kind of ramification, so we call that end G, that discriminant exponent, that those elements generate an abelian subgroup of the Galois group. We do that by using this approach and the strategy 1B here. I stated this because it happens to be a case in which we can kind of state a really nice criteria for which groups we prove the conjecture for, but I will say there are many other, it's not really about the group being nilpotent, it's just sort of an abelian subgroup. This same approach works for many other G, including, some things that might be like of the form of some representation, semi-direct product of a representation of a certain finite simple group. So I'm not going to say the conditions, but groups of this form. So it's not about being, it's not really about being nilpotent. It was just, it's easiest to state a kind of broad result because of the group theory of nilpotent groups in the nilpotent case. Okay. I'll just mention in words that we, this is for discriminant. We actually, you can apply this approach to many other ways of counting. We give a result in this paper where for every group with a non-trivial abelian normal subgroup, we give a way of counting such that we can get the asymptotic. So that's kind of, just this presence of, okay, in this case an abelian normal subgroup is enough to make this method work with some way of counting. So I would just end by saying that all this picture of this strategy was kind of agnostic to the counting invariant used when I say L over K. But of course, the actual work is not agnostic to the counting invariant, and what you can do very much depends on what invariant you're counting by. And to count G extensions by one invariant, you might need to be doing something like counting these L prime over K prime by a completely different invariant. And a crucial aspect of the work is being able to sort of count by different invariants and to modify the invariants that you are counting by. So Yeah, so that is true even in situations where the result that you care about in the end is a result of counting by discriminant. All right, thank you.
Much Melanie for this talk. Any questions?
Yes.
So your paper has what looks like to me to be some fairly serious homological algebra, recording results of Skinner-Urban, Greenberg-Wiles. Where does this machinery come to play?
Okay, so there are sort of different places that comes into play. I would say that you should, maybe the best way to think about it is in the simplest example, those homology or cohomology groups are just class groups, or torsion in class groups. And so if you're using this kind of, I shouldn't have need to raise it, that's kind of unfortunate, but if you're using this kind of inductive strategy, you, especially like if H is a abelian group and you're counting the abelian extensions, it very well may be that the thing that you need to sum, the number of abelian extensions, has, say, in that constant, something about the class group of the field that you're counting over, right? You're familiar that can come up in the constant for counting abelian extensions. Here, it could involve some part of the class group of K, and then you need to sort of sum those up and say something about the class group. And so, I guess what I would say is that in this, when I said being really good at counting abelian extensions in order to detect the full Galois group, what you're seeing in those cohomology groups and how we're working with them coming up is just the generalization of the class group that you need. If you were just counting H extensions, it might be the class group, but the generalization of the class group that you need to be doing this twisted counting, as Brandon and Evan would say, involve these cohomology groups. So I encourage you to think of them as just like, oh, they're kind of like class groups. They're just this twisted variation of them that you need for this, slight generalization of the question.
Questions?
Yes.
Yeah, fairly ignorant questions, but I'm going to ask. So you mostly talked about how you get to breaking up your sums, so you get to something you count. Can
Yeah.
you describe how you count when you count?
Yes, that is a perfectly fair question. So the methods in our paper, the strategies for counting are essentially the strategies that have, like for counting, say, H extensions, are essentially the strategies that are already out there. We just may have to do more with them because of what we need for our problem. So for example, we do a lot in this case where H is abelian. So the strategy here is that by class field theory, you can write down explicitly what the extensions are. And that has been done before in lots of cases. We have to do more because we need to do things like not just count the extensions, but detect if they have the full Galois group. But class field theory also allows you to do that in its explicit description of all the abelian extensions. In some other cases where we do, say, counting S3 extensions, again, the methods that we use to count the S3 extensions include, like using the Shindani zeta function, which is a classic way of counting S3 extensions. We have to maybe do a little bit more with that method because we have to do something like sum error terms. So in our paper, at least, I would say the methods that we use for counting extensions, are, in these cases, the methods that people were previously using, and we just have to go back to the methods and do more so that we can sum error terms, so that we can detect additional things about the extensions. Yeah.
Curious about
Yeah.
by using, you put up some sort of pseudo zeta function. Are you using analytic continuation for zeta function? You did some sort of combinatorics on a region to count lattice points.
Yeah. So so in the cases we're applying like this kind of strategy 1B, we're doing neither of those things. I would say instead of those things, we're using class field theory would be the way to describe it. In the cases where we're doing something like this strategy, I think that we have, in practice, like in the S3 case, used the Shindani zeta function. But yeah, possibly you could have used pre-homogeneous vector space methods.
I guess what strikes me is that when you get the asymptotic, you're essentially saying this zeta function can be analytically continued to the line 1 over A.
Yeah.
So, I mean, you might be able to even say it's analytical or variable from 1 over A.
Yeah.
You literally identify poles for that function. I don't know if you've gone down that kind of route of trying to understand.
Yeah. So we have not gone down that route, but that makes me want to mention, Alina, is your paper with Brandon out?
Yeah, oh yeah, as of like Tuesday.
Okay, a hot off the presses paper of Alina Bucher and Brandon Alebrts, where they are really thinking more about the analytic behavior and understanding the poles of the zeta functions associated to the different ways of counting, but in a beautiful way where they are using multiple Dirichlet series for all the ways of counting and really leveraging that in some interesting ways. So I would say in this work of mine with Brandon and Jiuya Robert, we do not consider that, but I would say the paper of Alina and Brandon, Alina Bucher and Brandon Alebrts is the kind of the first paper in that direction, trying to use some of these ideas, but in that way to understand the poles of the related Dirichlet series of counting these objects.
Yeah, it seems like in this inductive strategy, especially in 1B, it's like you're seeding your algorithm with something which we know how to do, which is often like a balanced or fair kind of counting. In this strategy, once you start doing things and you're inducting a lot on like subgroups, could you also turn around and say, oh, well, actually we should be changing our counting functions as well, and kind of like go back and forth between the two ideas and update your notion of like balance?
Yeah, but well, okay, all right. I'm not going to change the notion of balance. That was long negotiated. But, okay, all right, the thing is, we're actually really good at counting abelian extensions in all the ways of counting, not just the sort of balanced ways of counting. All right, so, I guess I don't know a good thing to answer, except that I think that what you're asking about gets to the somehow the flexibility and the number of choices in this method, in terms of you have this whole diagram and like, well, there are which ways you may be good at counting these extensions might then translate into being good at counting these extensions in a different way. And so that's kind of part of why I think this inductive strategy really promotes like counting by different invariants, because I mean, it's not even clear what it means to say the same invariant here and here because they're different groups, but Yeah, certainly what this approach does can take being sort of good at counting some kind of extensions by some kind of invariant and translate it into being good at counting another kind of extensions by different invariant.
Any other questions?
Yeah.
But since you're kind of assuming that a good invariant is one that's easy to count with, but I think it's very natural to say a good invariant is one that's hard to count with.
But wait, did I ever say the word good invariant?
You didn't say good. Okay, you did say that the balanced ones were easier. I think usually the balanced ones are harder.
I didn't say, I don't think I would have said the balanced ones are easier. I don't think that, no. Yes, okay, so very clearly, I want to be clear that I did not say that there were certain ones that were good, though I did perhaps say that some things like discriminant are natural for certain reasons. Some of them kind of have a natural meaning. And there is no doubt that some of them are easier in terms of having proofs than others. Absolutely, some of them are easier to do than others. And the ones we prove first, as a community, are kind of those ones. Yeah, I don't know if you want to revise your question. You can.
I agree. I agree that we should do all of the invariants, but that if you do the hardest invariant, then you probably can do all the invariants. So in that sense, it's good to do the hardest.
Yes, but I think that's sort of tautological. And that the hardest one is whichever one you prove last. It's like when you find your keys in the last place you looked. I mean, yes. So certainly you can guess which there are ways that you can guess which are going to be harder to prove, and that absolutely those are more more interesting. Yes, somehow, and yes, in some kind of tautological sense.
Any other question?